Dear students, today we will discuss applications of Gauss law. It means by using this Gauss law, we can find the electric field intensity due to various types of charged conductors. Therefore, this method has three steps. First one is imagine Gaussian surface symmetrical to given charged body. Means if you imagine or just take a spherical conductor. Due to this spherical conductor, if you want to calculate the electric field intensity, by using the first step, we have to imagine a Gaussian surface around this spherical shell that must be symmetrical to this body. Symmetrical means this surface, imagined surface, must be equidistant from this spherical shell. This is what the first step, and the second step is finding the electric flux through the Gaussian surface. The second step is through this Gaussian surface, what is the electric flux due to this shell. That is the second step, that is phi. Phi is equals to what? Through this spherical Gaussian spherical surface. Next, third one is equate this phi or equate this electric flux with Q by epsilon naught. That is, equate that electric flux to Q by epsilon naught. Here Q is the charge enclosed by this Gaussian surface. Here this Gaussian surface encloses the charge, this Q. It means this charged spherical shell has a charge Q. Okay, now these are the three steps, and by using these three steps we can find the electric field intensity due to various types of charged conductors. And now we have to calculate. It means by using one example, or with these three steps, we can find the electric field at a point outside the charged thin spherical shell by using Gauss law. Okay, these are the three steps involves this Gauss law or this method. Therefore, now we will see one example, that is finding expression for electric field at a point outside a charged thin spherical shell by using Gauss law. Now let us consider a spherical shell, a charged spherical shell. This spherical shell is having charge Q. And R is the radius of the spherical shell. Now by using R due to this spherical shell, what is the electric field at a point outside the charged thin spherical? Outside, it means this point must be outside from this spherical shell, is at a distance R from the center of the spherical shell. Okay, now see here, this is the spherical shell. This spherical shell has a radius R. R is the radius of the spherical shell, and O is the center of the spherical shell. Okay, and I am considering point P is outside from this spherical shell and also is at a distance R from the center of the spherical shell. Now P is the point at a distance R from O. Okay, now let us consider Q is the charge of the spherical shell. Now we have to find the electric field due to this spherical shell. Okay, to find this electric field due to this, I am considering the first step of this method. What is the first step? The first step is consider a Gaussian surface. Okay, or consider the symmetrical Gaussian surface. Now this is a symmetrical Gaussian surface. Now see here, you can see this surface is symmetrical to this spherical shell. Okay, and now at this point we have to calculate the electric field. Therefore at this point we have to consider, or we have to take a Gaussian surface. This Gaussian surface is at distance r from the center of the spherical shell. Okay, and now to find this electric field, or here E is the electric field produced by this charged spherical shell, and to find this one I am considering first small area, because we can't calculate directly through whole this surface. That's why I am considering first a small surface. Through this small surface, what is the electric flux, and after that we will take electric field. Okay, and now delta S is a small area. Delta S is a small area, and E is the electric field produced by the shell. Okay, now the electric flux through the Gaussian surface is, the electric flux through the Gaussian surface is, this is the Gaussian surface. I am considering a small area. Whole the surface means summation of delta S. Therefore phi is equals to E into summation of delta S cos theta. The summation of delta S means whole this surface. Therefore summation of E into delta S cos theta. Now you can see this electric field and the normal to the surface is, the angle between E and delta S are in the same direction. Are in same direction means theta equal to 0. Okay, phi is equals to summation of E into delta S. Cos 0 is 1. Therefore phi is equals to summation of E into delta S. Let us recall equation number 2, and this one is 1. And phi equal to, here E into summation of delta S. Summation of delta S means the surface area of this sphere. This is a Gaussian spherical surface. We know the area of the sphere, that is 4 pi r square. Why it is r? This r is the radius of the Gaussian surface, because summation of delta S is 4 pi r square. Now see, listen carefully. Now this summation of delta S, the surface area, whole the Gaussian surface area is 4 pi r square, which implies, or let us recall equation number 3. Now phi is equals to E into 4 pi r square, because summation of delta is equals to 4 pi r square. Now this is equation number 3. Okay, and next, according to Gauss law, now this is what according to the definition of electric flux. Now I am considering according to Gauss law. According to Gauss law, the electric flux is what? The definition of the statement of Gauss law. The Gauss law is 1 by epsilon naught, means the electric flux through the closed surface is 1 by epsilon naught times the charge enclosed by the surface. This is what the electric flux according to the Gauss law. Let us recall equation number 4. Now this phi equals to something. Now here also phi equals to something. Let us equate this 3 and 4. Therefore from 3 and 4, shall I equate these two? Okay, equate. E is equals to 4 by r square. E is equals to 1 by epsilon naught times and q. Now phi equal to this much, and here phi equal to 1 by epsilon naught times q. Now I am equating these two quantities. Okay, therefore E equal to 1 by epsilon into is 1 by 4 pi 1 by 4 pi r square into q. Just rearrange the terms. 1 by 4 pi epsilon naught into q by r square. 1 by 4 pi epsilon naught into q by r square. Okay, now this is what the expression of electric field due to the charged spherical shell is at a distance r from the center of the spherical shell. Okay, next we have to calculate the electric field just outside the spherical shell. Already we have calculated the electric field outside the spherical shell. Now we have to calculate the point is just outside the spherical shell, means there is nothing but on the surface, just outside or on the surface of the spherical shell. Then what is the electric field? We'll see now. Now see, let us consider a spherical shell. Spherical shell. This spherical shell has charge q and also it has a radius this r. Now our point is on the surface, means is at a distance capital R from the center of the spherical shell. Okay, therefore we have to calculate the expression of electric field E. The expression of electric field at a point just outside the charged thin spherical shell. Now see here, this is a spherical shell and R is the radius of the spherical shell and O is the center. And here we have to calculate the electric field at a point just outside the spherical shell. Here this P is the point. At this point we have to calculate the electric field. Okay, this is the direction of the electric field. This is the electric field. This. Let Q is the charge. This Q is a charge uniformly distributed over surface. Therefore, the electric field, already we know that the electric field due to charged spherical shell at a point outside the shell. Outside the shell is E equal to 1 by 4 pi epsilon naught q by r square. But here our point is at a distance nearly r, but here r is nearly equals to capital R, which implies E equal to 1 by 4 pi epsilon naught q divided by capital R square. Let us recall equation number 1. And we know that, and also we know that here the charges are distributed over the surface, that is uniformly distributed over the surface. We know that surface charge distribution sigma is equals to what? Sigma is equals to q by A. Here q is the charge, A is the area. A is the area means what is the area? That is 4 pi capital R square. This is what? The area of the spherical shell, which implies Q can be written as sigma into 4 pi R square. Okay, let us look at equation number 2. Now substitute equation 2 in 1. That is from 1 and 2. E equal to 1 by 4 pi epsilon naught q is replaced by sigma into 4 pi r square divided by r square. Okay, now this r is nothing but capital R square. Capital R square get cancelled. 4 pi which is equals to sigma divided by epsilon naught. E equal to final expression for electric field, E equals to sigma divided by epsilon naught. This is the expression of electric field is at a point just outside the spherical shell. That is E equals to sigma into epsilon naught. Okay, now we'll see graphically. And now we'll see the graphical representation of electric field with different distances from the center of the thin spherical shell. Okay, now I'm considering here the spherical shell, thin spherical shell. Now here, due to this spherical shell, what is the electric field at different distances? Okay, now first one, at the center the electric field is 0 because inside the spherical shell, not only center, inside the spherical shell the electric field is 0. That is when r is less than r, when this distance is less than r, means your point is inside the spherical shell, that electric field is 0 at center, or when r is less than r, the electric field is 0, means up to the radius of the surface the electric field becomes 0, the electric field is 0. Okay, next, when r is equals to r, means your point is on the surface of the spherical shell. If the point is on the surface of the spherical shell, means small r is equals to capital R. That means the distance becomes the radius of the spherical shell. Here the electric field E is equals to 1 by 4 pi epsilon naught q by r square. And similarly, if the distance goes on increasing, means your point is outside the spherical shell. In that case, what is the electric field? That is E equals to 1 by 4 pi epsilon naught q by same, that distance is r square. Here this electric field is inversely proportional to square of the distance. If the distance is increasing, the electric field goes on decreasing. That's why here in this graph we can describe here. Now up to O to R or up to R, your E is 0. This is 0. And when the point is on the surface, or if the point is on the surface, the electric field becomes maximum. This is the maximum electric field. Okay, and if R goes on increasing, means when R is greater than R, this electric field goes on decreasing exponentially like this. And finally, when R is equals to infinity, when this R is equals to infinity, then what will happen? Substitute R equals to infinity, q by 0 or anything by 0 is infinity, means electric field becomes E is equals to 0. Here R is infinity, sorry, anything by infinity is equals to 0, that is equals to 0. These are the different electric field due to different distance with different distances. In next class we will discuss the expression of electric field due to infinitely long straight uniformly charged wire by using Gauss law. Means by using Gauss law we can calculate the expression of the electric field due to uniformly charged wire. Okay, thank you.